So in this case, we are given the formula, some IR data, and the NMR spectrum here. So compound O has a formula C10H12O, and again, we're going to figure out the HDI, 10 times 2 plus 2 minus 12 all over 2, and that is equal to 20 plus 2 is 22 minus 12 is 10 divided by 2 is 5. And as we've said, anytime we have a HDI value of 4 or greater, there's a high probability that we have an aromatic ring. And we can confirm that we have an aromatic ring by looking in the aromatic region of the proton NMR spectrum, and we see hydrogens there. In this case, we see 5 of them. So that's a pretty good indication that we might have a mono-substituted aromatic ring. So let's look at the rest of our NMR spectrum. We see 3 other signals, a triplet worth 3 hydrogens near 1, and another triplet worth 2 hydrogens at 3 ppm, and then this very interesting arrangement around 1.7, 2 hydrogens. This looks like it has 6 peaks here, so we call that a sextet, and that means n equals 5. So that the hydrogens that have created this signal at 1.7 are next to 5 hydrogens, which are probably these 5 here. So most likely we have a CH2 that is next to a CH3, probably this CH3, and another CH2, and that would be this CH2. Does that make sense? Well, if the green CH2 is where we think it is, it would be split by the blue CH2 into a triplet, and indeed we have a triplet. And the red methyl group should be split into another triplet by the blue CH2, and indeed we have a triplet here. And then of course, when n equals 5, 2 plus 3, we would expect a sextet type splitting pattern for the blue CH2, and indeed this should be the blue CH2. What are we missing? Are we ready to put this together and put a propyl group off of our aromatic ring? I have 6 carbons here, 7, 8, 9. I need 10. I have the IR absorption at 1687, and I have a missing oxygen, I think. And so probably I have a carbonyl, and the only place I can put the carbonyl is right off the aromatic ring, and then I can add the propyl group. And I think that's a pretty good structure for compound O. Let's confirm here. This CH2 should be chemically shifted pretty far from the normal 1.2 ppm chemical shift, and that's probably going to be this green CH2 shifted up to 3. I believe that is probably very much the case. And then of course the red methyl is right there. So I hope you agree with me about compound O. Let's take a look at compound P. We're given a more interesting chemical formula now that has fewer hydrogens, but it has a chlorine. So C5H9Cl O2. The HDI count is 5 times 2 plus 2 minus the hydrogens minus the chlorine all over 2. And if we do that, we have 10 plus 2 is 12 minus 10 divided by 2 is 1. So we do have 1 HDI in this case, probably a double bond, less likely a ring, but we'll investigate a little more. We are not given any IR data, but we are given the carbon-13 NMR of compound P, and we see that it has 5 distinct carbons. That means that all 5 of these carbons are different. There is no symmetry in this molecule. We can also deduce the presence of a carbonyl because this carbon signal at 170 is in the carbonyl region. Remember that the carbonyl region is between 150 and 200, sometimes even a little beyond 200. So most likely we have a carbonyl right here that accounts for our HDI, and it accounts for one of the oxygens and one of the carbons. Then we have 4 other carbons, and we probably have a carbon next to an O and a carbon next to a chlorine, because the chlorine has to be attached somewhere. So let's move on then to the proton NMR. We see 4 proton signals, 3 hydrogen signal, that is probably a methyl group. That's a triplet. We see a 2 hydrogen quartet way downfield past 4. That is very indicative of an O ethyl group. We've seen that before, and we'll continue to see that setup. So this is most likely an ethoxy group. Chances are it is an ethoxy group connected to the carbonyl, so a ethyl ester. That leaves us then with the 2 CH2 groups that are both triplets. And remember, we've seen this setup before as well. This CH2 is a triplet, so it has to be next to another CH2. And so in this case, we have this setup with those 2 CH2 groups. And I know that the X's do not have any hydrogens attached to them because my CH2s right here are only triplets. So those X's do not have any hydrogens attached to them. The last thing that I'm missing, I believe, is the chlorine. That attaches somewhere. And then, of course, I have my CO. And I think that accounts for everything. I have 1, 2, 3, 4, 5 carbons. That's all I have. I have 2, 5, 6, 7, 8, 9 hydrogens. That's the max. That's the hydrogens I'm given. I have the chlorine, and I have 2 oxygens. Now let's put all these pieces together. I think, like I said, that I have an ethyl ester, given the high chemical shift of my CH2 group as part of the ester, and that just leaves the 2 CH2s and the chlorine to add. And I really can't put them together any other way and still have a complete molecule that matches my chemical formula. So I believe that this is the best structure for compound P.